The next presentation is by Professor Duchesne on the challenges of in determining the deleterious potential of sulfide-bearing aggregates in concrete. Professor Duchesne is a professor at Laval University, specialist in microanalysis, sulfate attack, AAR, and lots of deleterious mechanisms. So please come in.
Okay. Thank you, Pierre-Luc. Good evening. Tonight I will speak about the challenges in determining the deleterious potential of sulfide-bearing aggregate. But first I would like to thank my co-author, Benoit Fournier, Andreia Rodrigues, Julie Francoeur, Benoit Durand, and Medhat Shehata. This is the outline of the presentation. Oops, sorry. First, I will give you some background, example of deterioration, petrographic examination, overview of oxidation reaction mechanisms. Then I will show you a few outdoor exposure sites, and then I will show you the performance-based protocol developed over the year with the total sulfur content with petrography, oxygen consumption tests. I will speak about a mortar bar expansion test, and finally I will show you the few lines of the new project. More than 2,000 residential owners in the Trois-Rivières area are facing serious issues related to their concrete foundation. They had a lot of problems, cracking, and in the foundation walls and slabs on grade. I will show you a few examples. The deterioration was very rapid, 3 to 4 years after the construction, with a lot of cracking on the walls. You can see here the cracking were filled just to avoid water coming into the foundation. You can see here the crackings, sometimes with yellowish coloration, and the cracking can be very huge, and the deterioration is very rapid. You can see inside the houses a lot of cracking, but also pop up with oxidized aggregate particle. We have a lot of oxidized particle with whitish products around a rim around the aggregate particle. The only way to repair is to replace the foundation. Then the houses are left, the foundation are demolished and rebuilt. I will show you a few examples of the petrographic examination of the aggregate, but also of the concrete. We will show you a macroscopic examination, microscopic with light microscopy, also with a scanning electron microscopy, and finally with electron probe microanalysis. This is the quarry. The quarry with, you can see some oxidized particle into the quarry. We had the thin section observed on plain polarized light, where you can see the particle in black. That's the sulfide mineral. Sometimes they are surrounded with biotite, which is mica. This is a cross-polarized light. The rock in the Trois-Rivières area, it's intrusive mafic rocks. It's a type of gabbro. It's enriched with hyperstein. And here you can see on the reflected polarized light the sulfide minerals. Here you have the pyrite and also pyrrhotite. We have a small amount of pentlandite too. This is a backscatter electron image. This will show you the contrast and density of the different mineral phases. You can see that the pyrite here and the pyrrhotite. The pyrrhotite is denser than the pyrite. This shows you the energy dispersive spectrum of the pyrite minerals. The pyrite is iron sulfide with a ratio of about 47% iron and 53% 54% sulfur. This is the signature of the pyrite. Pyrite is also a iron sulfide mineral, but the ratio of iron is, for the pyrite, the ratio of iron is higher here with 62% iron and 38% sulfur. But both are iron sulfide mineral. This is a chemical map done with the microprobe. The first map, it's a backscatter electron image showing the density of the different mineral. The first map here, it's a calcium. You can see here the calcium on the aggregate particle. This is the map for the iron. With in yellow, it's the higher content of iron. Here you have the nickel map. Most of the nickel is into the pentlandite. And here you have the sulfur. You can see that you have different amount of sulfur into the aggregate. And finally, we have a reconstructed map showing the mineralogical phases. You can see that the pyrite here, pyrite in orange. You have the chalcopyrite, the pentlandite. We have a small amount of calcite into the pyrite grain, and finally the feldspar, which are rich in calcium. I will show you a few examples of the petrographic examination of concrete sample. You can see on the concrete core that most of the aggregate particles are rusted. And you can see here the particle with the sulfide mineral. Sometimes the sulfur mineral are completely rusted, and we can see different reaction products. Most of the oxidized particles are surrounded with a rim of a whitish materials, and we have done a lot of experiment on this material to identify the secondary minerals. And we can see that the pyrite, in presence of oxygen and water, oxidize, giving goethite, which is iron oxyhydroxide, and this reaction produces sulfuric acid. And then you will have an internal sulfate attack. With the sulfuric acid in presence of portlandite will produce the gypsum, and we can see gypsum in the secondary mineral phases. Gypsum is calcium and sulfate. With the aluminate of the cement phase, the reaction with the sulfate and the water will produce ettringite. Ettringite with its calcium, sulfur, alumina, and oxygen. This is a really expensive minerals. And then the last one, it's the formation of thaumasite. In presence of sulfate with carbonate and with the CSH and water, we have the formation of the thaumasite. Here you have an XRD pattern showing that both ettringite and thaumasite are present into the reaction rim around the oxidized particle. Both are needles-like minerals. Thaumasite, it's shorter than the ettringite, but most of the time both are mixed together. We also work with the concrete blocks from the houses, and we put the blocks in outdoor exposure site to measure the expansion, the monitoring of cracking, and the sampling of blocks. I will just show you a few examples. We selected different houses according to the damage at the moment of the demolition. We had 4 different types of damage with the code 0 when there were no visible damage. This was mainly in the party wall between the semi-detached houses. We have low cracking, It's number 1. Number 2, it's cracking with wide less than 2 millimeters. And finally, grade 3 with crackings between 2 and 12 millimeters. We measure the expansion, and according to the rating at the beginning, here you have a level 0 with very low expansion, and the expansion just increased at the end of the experiment. Here we have concrete blocks with a rating 2, and you can see the expansion. It's very important, and the expansion has a good correlation with the density of cracking. We measure the density of cracking, and we can see that the expansion and density of cracking, it's in good correlation. We also do a lot of testing and sampling just before the demolition of the foundation. We measure at different levels into the foundation, and we measure the relative humidity. We measure the sulfide content into the aggregate, the damage assessment with different mechanical, physical, microstructural, different kind of tests to try to identify the problems, and also to tend to correlate between all these factors. We also develop exposure site with the reactive aggregate, the aggregate from Trois-Rivières, but also other sulfide-bearing aggregate, and with different type of concrete mixed designs. And we monitor the cracking and the expansion. The blocks were made in 2012, and in 2018 the first cracks appears. And we've done a large laboratory testing program with 8 different sources of aggregate. We measure the total sulfide determination. We evaluate the mineralogy with Petrography. We had a test of oxygen consumption test and an expansion test. I will just show you the main result of all these test programs. This test program is part of the performance testing for sulfide-bearing aggregates. We develop a protocol. The first step in the protocol is a measurement of the chemical. It's a chemical testing to measure the total sulfur content of the aggregate. This total sulfur content, it's measured with a sulfur carbon analysis, where you measure the sulfide content of the aggregate, and we also look if pyrrhotite is present into the aggregate. The first step is this measurement. If your total sulfide content is higher than 1%, the aggregate is rejected. If it's lower than 0.1%, we can accept the aggregate. If it's in between the two, we have to go into the second step if the aggregate contains pyrrhotite. If the aggregate don't contain pyrrhotite, then we can accept the aggregate. The step 2 will be the oxygen consumption test. I will show you the test. This is a chemical test where we put the aggregate into a closed cells, and we monitor the amount of oxygen in the headspace of the closed container. We monitor the oxygen concentration during 3 hours. The aggregate here, it's in a very fine particle, and it's mixed with water to have 40% saturation. And in this protocol, we use 10 centimeters of aggregate particle, and we use 10 centimeters of the overhead, and we measure the oxygen 3 hours monitoring of the oxygens. I will show you just few results here. We have these control aggregate without sulfide. they don't really consume oxygen. This is the aggregate from Trois-Rivières. This is a very rich pyrrhotite type aggregate and different other material containing sulfide-bearing aggregate. For the moment, we put the limit to 5%, but this limit was fixed with only 8 different type of aggregate. We need to test more type of different aggregate. Then here, if the oxygen consumption is higher than 5%, we have to continue to step 3. If it's lower than 5%, we can accept the aggregate. And then we go to an accelerated motor bar test, which is a test similar to the test used in ASR testing on motor bar. That's the same type of motor bar, but the conditions are really different. The first step of the test, it's 80% relative humidity, keep at 80 degrees, and the samples are soaked in bleach 2 times per week, and then the test continue for 90 days. After that, we put the motor bar, at 4 degrees, 100% relative humidity. We continue to soak in bleach 2 times a week. The first step, it's a step for the oxidation of the sulfide-bearing aggregate, while the second step at 4 degrees, it's to produce the thaumasite. These conditions at 4 degrees, 100% humidity, are the best conditions to promote the thaumasite formation. While the first step is to produce the sulfate from the oxidation of the sulfide-bearing aggregate. And then these are the result. In the first step, the pKa, it's a control. It's a control aggregate without any sulfide minerals. And you can see that the control don't increase, and but the problematic aggregate start expansion in the first part of the test, but the expansion increase a lot in the second part with the formation of the thaumasite. You can see here the control. The control is okay, no cracks, nothing. But for the reactive aggregate, we have crack beginning there, but at the end, the motor bar are completely destroyed because of the formation of the thaumasite. Then, for this step into the protocol, if the expansion is higher than 0.1% after 90 days, then we transfer to 4 degrees, and if the expansion continue, then the aggregate cannot be used. The second step is really important, the step at 4 degrees. Here we put a step at 4 degrees because I don't have the figure here, but alkali-silica reactive aggregate we increase in the first part of the test, because we had aggregate with both problematic. They were alkali-silica reactive and they were sulfide-bearing aggregate too. But in the first step, it's really good for ASR too. But if it's just ASR, the expansion will be high after the first step, but won't continue after that. They will have a plateau after that. But we need to try more to separate both types of mechanisms. And then I will just present you a few objects, the aim of the next project. We had a research chair found by the NRC, which is the National Research Council of Canada, the Quebec government, and the Université Laval. We will continue the project with one master student, 4 PhD students, 1 postdoc, a research professional at Université Laval. The research will be carried out in NRC and also at Laval. And we will have 7 masters across Canada to test different type of aggregate. The main objective of the project was to determination of acceptable limits of sulfide minerals content in Canadian aggregate, to develop a rapid and reliable test for detection of deleterious sulfide content in concrete aggregates, development of preventive measures, development of technical capacity to carry out tests, develop the test developed here in Canada, and the revision of the testing protocol for the CSC standardization. Thank you for your attention.
So is there any questions for Professor Duchesne?
Yeah, thank you for your presentation. I wanted to ask, in your opinion, should the focus be on primary oxidative products or the secondary mineral formations?
I think that both are really important because the oxidation of the aggregate particle will produce the sulfate, and then the sulfate, it's an ethanol sulfate attack. You have sulfate, if you have carbonate in your mixture, humidity, and then the CSH, the silica will come from the CSA, and then you will have the thaumasite. If you have aluminate, citrate A, high citric content, and then you also have the heterogate. But the thing here is you don't need aluminate for the formation of the thaumasite, and that's the bad thing. And if you have a limestone filler concrete, you will have more carbonate present in your system. Then if you have sulfate from the oxidation of the sulfide with high humidity, that can be a huge problem.
When you find your heterogate and thaumasite, are you finding it in within the paste or in voids, and like kind of what magnitude? You didn't have a magnification or a scale bar. Where is it from?
They are in the paste, in the reaction rim around the aggregate. And it's a mixture. We are not sure if it's a mixture of heterogate and thaumasite, but we think that it's a solid solution between both two. Yeah.
Are you finding that you at 5,000x, 10,000x?
Oh.
You find that? How
I should ask to Andreia. Yeah, but it's in the whitish around the aggregate particle most of the time.
So it seems like this is a very localized problem. Like here in Quebec, we have a problem, and Connecticut we have a situation. So it seems more like an ACR type case where you identify the quarries, which are the problem quarries, and avoid it. So should the protocol be something like ACR's protocol? The other thing would be that for ASR, you test all the aggregates.
Yeah.
Right? So which protocol? Is it the ACR
Okay.
protocol or ACR?
Yeah.
How do you think, looking forward?
Yeah, I understand your point, but the pyrite and pyritite are they are not rare. You have a lot of different type of rocks containing pyrite and pyritite. But it's a question of content. It's a question of surface area and condition. That's why we try to develop a protocol. Why developing a protocol? Because it's really difficult to quantify the amount of pyritite into a concrete, because it's an iron sulfide. Pyrite, it's an iron sulfide too. Chalcopyrite, it's a copper, iron, and sulfide. There is a lot of different minerals containing sulfide and iron, and it's difficult to quantify. It's like saying that, can you just measure the silica content of your aggregate to know if it will be alkali silica reactive or not? I think there is too many sink of silica into an aggregate particle to be able to detect ASR according to the SiO2 content. I think that's about the same thing here, because you have a lot of aggregate particle with sulfide, pyrite, or pyrite and pyrrhotite and other sulfide minerals. Okay, thank you.